So thank you again for your patience, and thank you for your attention, and thank you Grazina and Dagmara for inviting me here to introduce you to asteroids and show you how exciting they are and why I think everyone should study them. My name is David Polishook. I'm an astrophysicist from the Weizmann Institute of Science. This is in Israel, and I've been studying asteroids for 20 years now. And I guess, my guess is that many of you, or most of you, came to study asteroids because they impose danger to the Earth. This is what makes asteroids a very, let's say, sexy subject. Like in this event, what you see here is a real asteroid entering the Earth atmosphere. It happened 8 years ago, about 40 kilometers above the city of Chelyabinsk in Russia. A 20-meter size asteroid exploded, forming this amazing glare of light and produced a shockwave that destroyed and shattered the glasses and windows and roofs, causing more than 1,000 people to get injured. Of course, so these impacts can happen, and asteroids are, if are larger, they can form craters, they can kill dinosaurs, they can make Hollywood movies, save the world, etc., etc. I'm not going to talk about any of this really exciting topic. I will leave this to my friend Christina Thomas to talk about this later on. I will talk about asteroids in another point of view. I will talk about asteroids as just a minute, as a piece of a cake. What do I mean? Not just a piece of a cake. The leftovers, the crumbs that you see on a plate, understanding that someone is eating your cake. Because we are a great astrophysicist, using our detective skills, we can learn from a plate like this what was the size of the cake, what was the ratio between the chocolate and the cream, how tasty it was. So this is what asteroids are, the leftovers from a cake. And of course, I mean that this is as a metaphor for the formation of the solar system. Asteroids are the leftovers from the formation of the solar system, and our job is to try to collect all the pieces and to understand what happened here 4.5 billion years ago. But let's start from another start. Asteroids were the first asteroid was discovered only 220 years ago by this gentleman, Giuseppe Piazzi, astrophysicist and mathematician from Sicily. And he wrote in his diary about his discovery done at the 1st of January, 1801, where he found a star that a new star. He did not saw it in his catalog, and the star on the following night advanced by about 3.5 arc minutes, and he thought at the beginning that it is a comet, but then since it showed no nebulosity, no coma around it, he understood that it could be something even better than a comet. And what is something better than a comet? Well, a planet is very nice, but this is something even better than that, an asteroid, something that was first found by this guy. I should say that Piazzi followed this, before that. What you see here in these very few lines is that very few lines is the definition of asteroids. Bodies that are that are close to us, nearby, therefore the motion is apparent, and they have no velocity. Okay, so they are like stars. asteroids in Latin. Herschel, the famous astronomer that discovered Uranus, he named them as asteroids. This specific one is called Ceres, or 1 Ceres, the first asteroid to be discovered. Giuseppe Piazzi followed this asteroid for about a month and a half, and after a while, this asteroid was hidden by the glare of the sun. Yes, it went beyond the sun, and it was lost. And very fast, other astronomers started to have a suspicion: was it a real discovery or not? This and that person suspects that the observations are very wrong. So, but Ceres, of course, was right. This just comes as an example for us to have faith in our observational skills. And by the way, how this asteroid was refound? It was refound by Friedrich Gauss, no less than Friedrich Gauss, a famous mathematician that used his own method of minimal squares in order to fit an orbit around the sun for this object. So very basic mathematical method that we are using for so many stuff was actually originated from asteroids. So this is nice trivia thing to know. So asteroids are moving pretty fast, as you can see here. This is a short clip I made. I observed some time ago. Basically, the angular distance or angular velocity of this object is determined by the Earth motion and the asteroid motion. So Earth moves in about 30 kilometers per second. Most of the asteroids move in the 20 kilometers per second. So more or less, since the distance to most of the asteroids is about 1 AU, 1.5, 2 AU, we're talking about half of arc minute per hour. So at one night, you can definitely see, or even 1 hour, you can definitely see an object move like this. And of course, if we are closer, what we call near Earth asteroids, they will move faster. If they are farther away, like in the case of Kuiper belt objects, they will move slower. And now, maybe I'll have your participation here. And now, since you are a great asteroid hunters, you can point to the asteroid here in this image. Can I hear you? Maybe you can open your mics. Can you see some asteroids here?
Yeah, I can actually see 3.
Yes. Yeah.
So you see 3. Okay. Can someone see even more? Huh? Nice. 1. Yeah, this is good. This is the large one. Can you draw more lines on the other asteroids? Go ahead. Yeah. Number 2. Okay, I'll show you more. So this 1, 2, this is the third one over here. 1, 2, and another one here. So the sky is full with asteroids, moving asteroids all around. I can watch this type of pictures again and again and again. I really like it. Okay, let's move on. So maybe we can just clear all the drawings. Hop, here we are. Good. So a nice, this is a side note, is a nice privilege that people that discover asteroid have, is that they can give a name to asteroid. This is nice. This is, for example, like a data sheet of the orbit, observational details of this asteroid 172425, and the discoverer of this asteroid is name of the Polishook, very similar to my name. Interesting. Gave this asteroid. Come on, my guy, it got stuck. Just a second. Of course. Just a second. Okay, you can say it now. Yeah, so gave this asteroid a name after this person, Talia Jacobi. She was a medical student. She liked astronomy. She saw the 2004 Perseid meteor shower. She made the discovery of this asteroid, and the two fell in love. They were even married some 13 years ago, and this is a picture from the event. As you can see, asteroids are very exciting because they can take you to really strange places like weddings, etc. So who knows what will happen to you after you started to study asteroids. Okay, let's go back to business. So of course, you can't take picture after picture and look for asteroids. You can do it these days with smart computer code using data from surveys. So you observe the sky again and again and again, just somewhere in space, and you are looking for moving objects. One of the ways that we did it some times ago using data from the Palomar Transit Factory. This is a big survey operated in Palomar Mountain in California. So what we did was to form like a reference image by stacking all of the images together. And from every image, we removed this reference image, and we basically got all the sources of light that we could not see in this reference image. And when you take image after image taken time after time, you started these lines appear very fast. So these are asteroids that we could find. So many objects, so many asteroids appear there. The main two prominent surveys are called Catalina, and this operates in Arizona, and the Pan-STARRS from Hawaii. They have pretty large, or let's say, they have the larger telescopes used in these fields, meter, 2 meter wide, about 1,000 square degrees. This is the main parameter. What is the field of view that you cover within, let's say, within time, within a night, let's say. They can see pretty faint objects, 21, 23. Of course, everything is automatic and operating in real time. So you can, they can find objects and can send other telescopes to observe these asteroids as they are found. And this person here, his name is, I think, Richard Kowalski, if I'm not mistaken, is working in the Catalina Survey. And what's nice about his story, that he, I think, is the only person in the world that discovered a heavenly body, in this case, an asteroid, and he can hold it in his hand. So he holds a fraction of the asteroid that he discovered, because this asteroid impacted the Earth only a day or two after it was discovered. I'll show you later on this asteroid. So the data discovered asteroids, or let's say such survey started to work in 1998. Before that, we had a really slow rate of new discoveries. But since 1998, we start to have this explosion. What you see here is only near-Earth asteroids, but even main belt asteroids, the discovered numbers are even much higher. Here they are divided by their sizes. Do you know what happened in 1998? Why these surveys started there? Well, it's a really funny reason. Because of these movies, these famous movies, Armageddon and Deep Impact, were released in 1998. The American Congress got alarmed, said, oh, we must save the world. They gave NASA the money and the order to discover all these objects, and NASA organized these surveys. And as you can see, number of asteroids discovered is getting larger and larger. So what do we know until now? What do we know? What asteroids do we know? We know many of them in different orbits, and this is some kind of a list. What you see here is a logarithmic map of the orbits of asteroids. So the Sun here is here in the middle, Mercury, Venus, Earth, Mars is here, Jupiter, here is Saturn, and all these dots are asteroids. So what do we, let's go from the inside outward. So inside we have what we call near-Earth asteroids. These asteroids cross, their orbits cross the orbit of the Earth. By now, or by yesterday, there were 26,712 objects like this. Of course, there are much more. As you go, since there are more small objects than large objects, with time you discovered more small objects, more and more objects as your telescopes are larger and as they are better. This number seems like a large number, but the second group, the main belt of asteroids, is much more denser with asteroids, and much more objects. So it's about, now we know about almost 900,000 objects there. Of course, there are billions. Again, as you go farther, it's harder to see more and more. Then we have two groups on the orbit of Jupiter, what we call the Jupiter Trojan asteroids. Let's say 10,000, of course, more than that, 10,000, 7,000 that we know about. These objects lay in a stable orbit on the orbit of Jupiter. And they are stuck there. And following that, we have what we call the Centaurs, very few objects, and the trans-Neptunian objects. So all of the objects that are behind the orbit of Neptune. This includes the Kuiper belt. I guess you heard these terms, the Kuiper belt, and the Oort cloud, which is like a cloud of objects, a theoretical cloud of objects outside of our solar system. So now you see the numbers, and so you have a sense of what we are dealing with. Now it seems like a lot. It seems like this is a major part of our solar system, but this is wrong. Because when you take all of these objects and you put them in one basket and you measure the mass, you find out that they're basically very, very small. Their mass is insignificant to the mass of a planet. For example, here, compared to the mass of the Earth, yes, 1 in 10,000 mass of the Earth, 4% of the mass of the Moon, a third of the mass of the entire asteroid population is the mass of Ceres. So you can understand, even though there are so many of them, their mass is really small. And this instantly raises a question. How come their mass is so small? Why? We have here the orbits of the Earth, of the inner planets, Mercury, Venus, Earth, Mars, very close to one another. They are very massive. Where are all the masses of planets that was supposed to be here between the orbit of Mars and Jupiter? Where is it? So something happened to this mass. This mass was depleted at very early times of the solar system. And if we try to understand how the main belt of asteroids were formed, we can have maybe two ideas, and in these two scenarios, the mass disappeared. So one option is that the main belt was formed from material that never made it to build the planet. Okay, so material that never managed to accumulate into one another and build a planet like the Earth and Venus, etc. Or we had a planet there, or small-sized planet, planetesimals, and these planetesimals were destroyed by a catastrophic collision and destroyed. In both cases, where is all the material of the main belt? What happened? So we are stuck, if you want, with this plate with just a few pieces of the cake that is left over from the person who ate it. So who ate these asteroids? Where did they went? So this is one question we need to remember all the way to the end of this talk. Okay, we'll see something else here. What we'll see here is that the few numbers of asteroids within these two groups, the inner one, the near-Earth asteroids, and these centaurs. So objects there, well, definitely near-Earth asteroids, it's very close to us. We should have seen, we can see much smaller objects compared to the main belts. Same goes for the centaurs compared to the TNOs. The fact that we don't see very lot of asteroids is because these areas don't have a lot of asteroids. And why? Because these orbits, objects there, have orbits that are unstable. Their lifetime is about 10 million years on average. This, and since our solar system is much older, 4.5 billion years, this means that material keeps on going to these two areas from the stable areas, from the KBO areas, or maybe from the mainly from the main belt areas where we have most of the material. So this means that this area, mainly the main belt, is a source of material, so material can leave it. So we should go into the main belt in order to understand why. So when we look on the plane or the space plane of semi-major axis, meaning let's call it the average distance to the sun, compared to the inclination of the orbit of the asteroids. Same thing we'll do semi-major axis compared to the eccentricity. We'll see that the main belt is actually built of many groups. And more than that, well, before that, we'll see that in terms of inclination, asteroids are spread to high inclination of, let's say, 30 degrees. When you look about, if you say, there was supposed to be a very large planet, or the material there never made it to make a planet, still planets orbit the sun in average inclination of 2 degrees. How come these asteroids have this large range of inclination? Same goes for the eccentricity. Eccentricity of planets is about 5%. Eccentricity of asteroids can go to 30%. Okay, so what's going on there? So something happened to the orbits of asteroids that made them excite. So they became their orbits got let's say wild, if you want. How come? Well, maybe the solution comes from another thing that we can see here. We can see here all these gaps. Here you can see the same plot. Here is another kind of, this is a distribution. It's not compared to the inclination or eccentricity. And you can see that the main belt is like cut. Someone came with a knife and cut these pieces. How come? What are these gaps? These gaps are called Kirkwood gaps after a astronomer that discovered them called Daniel Kirkwood back in the 19th century. These gaps are, it's very easy to see, but they are in resonance with Jupiter itself. So an object, a test particle that will be put here at about 2.5 AU from the sun, will orbit the sun, will orbit 3 orbits around the sun, while Jupiter makes a single orbit. Jupiter is here at 5.2. This means that when you are at resonance with Jupiter, the gravitational torque that it puts on you, that Jupiter puts on the test particle, is only increase. It does not cancel itself when with time. This means that Jupiter can very fast push an object from these gaps, these Kirkwood gaps, can push them into the inner solar system or out from the solar system, making them near-Earth asteroids or this Centaurus group, or even push them completely outside of the solar system. So anyways, or near-Earth asteroids are basically main belt asteroids that enter these resonances somewhere million years ago, 10 million years ago, 100 million years ago, more or less. Okay, good. So maybe the reason, so I'll say one more thing. So asteroids in these gaps are in dangerous place. They are doomed. But asteroids in the other area, they are safe. They can stay there for billions of years. So therefore, how come these asteroids change their eccentricity and their inclination? How come they got excited dynamics? So if only we could take Jupiter and move it a little bit in order to make their eccentricity larger, this could be a good solution. Okay, maybe we'll think about it until the end of this talk. Now, I lost track of time. So, Grazina, are you still there?
Yes.
So, when you feel that it's time for the break, just tell me, okay?
We expect you to talk continuously for 1 hour and a half.
Not a problem. I'll talk for 1 hour and a half. Okay. Just a minute. Yes. Okay. So let's continue. So until now, we saw the orbital classification of asteroids. So in our solar system, we have near-Earth asteroids, then the main belt, the Jupiter Trojans, the Centaur asteroids, and then the TNOs, the Oort cloud, the KBOs, scatter disks, etc. Let's talk now about another type of classification, the compositional classification of asteroids. Do you have a question there?
Yes, I have a question.
Yes, please go ahead and ask.
Yes. What is the difference between centaurs as asteroids and comets? Because, for example, 29P is a pretty active comet, and it's considered as a Jupiter family comet, and at the same time as a centaur object. So, what's the difference, and is it the same or?
So, in a sense, I like when I talk about it, I say asteroids and comets are cousins, like relatives. The main difference starts with what Piazzi had to say. So comets have this nebula around them. This comes from their composition. So comets are rich with ice. It's basically ice with a lot of dust, a dust that is captured within the ice. Is this the case for asteroids? Well, first, in terms of composition, we'll need to see actually now. Okay, in the next slides. In terms of orbits, well, let's say the centaurs and the KBOs, Kuiper belt and Oort cloud, etc. All these have, let's say, more or less spherical orbits. Comets have very eccentric orbits, so they can come from all the way from the Kuiper belt, or I don't know, from the Centaur space, all the way to the inner solar system. And then the ice is evaporate, the dust escapes, and you have this coma and nebula and tail. So maybe some of these centaurs are actually comets that are just stuck there very far away, and they don't have these eccentric orbits. Maybe they are, maybe they are not. Maybe in terms of composition, they are more like asteroids. And they share, let's say, more or less the area of comets. So in order to know that, we need to get more information about the composition that we'll know now. So in a way, sometimes the classification of this between these different types of objects comes from, a very small window. Let's call it the astronomy window, but actually they are similar, or they're similar in some of the parameters. and sometimes, like only later on, you find that these are actually the same thing, just with like one small parameter making difference between them. So let me continue. Maybe we'll find more connection to comets later.
Another question, please.
Yes, please. Who is asking the question? Can you say your name?
BC Bernard Ogunwale.
Okay.
In the second slide, you asked us to identify the asteroid on the night view. I'm an amateur astronomer, so I want to know how you were able to pinpoint the one that are asteroid on your slide.
Wow, I'm not sure I understood the question. Which slide was it? The second one you said?
I think second or third slide. You asked us to identify the asteroid on the view, from the view.
So just stop me. It's like here, you mean?
No.
No.
See far further.
Farther on, you say. Not this one.
Oh, okay.
Even this one.
Not this. Okay, let's use this. Let's use this. Okay, fine. Let's use this. Okay, fine. Exactly this. Now, how do we identify the asteroid from the view, as in from this?
Okay.
This view now.
Yeah. So, well, basically, you have here, I think, like 10 pictures, and they are just put them in a small clip. The asteroids will move much faster compared to the background stars. So the background stars are basically fixed. Well, you need to wait for thousands of years for them to move, and you of course don't have this time. Asteroids, their apparent motion is pretty fast, as I said here, like about half arc minute per hour. So if you take a set of a few pictures, you will see them moving. Okay, same things for here as well. Okay, so here there are only 3 images. Their motion is pretty easy. Another thing you can do, by the way, for example, what I do when I need to observe, to do spectroscopy of asteroids, and I need to recognize which is the asteroid, I take a long exposure. If the asteroid is fast, so I will see the asteroid that is forming a line, a strike for me, like a line of light. If the telescope move with the rate of the asteroid, and some telescopes do so, so only the asteroid will be spherical, and all the other stars will become lines. So this is a way to distinguish these asteroids. Is this okay? Was it understood?
Yes, I'm okay. Thank you. Yes.
Excellent.
Thank
Good. Okay. Let's move on. So we were talking about a compositional classification now. What we can learn from the composition about the history of this cake, about the history of the formation of the solar system. Okay, so the best way to know how asteroids, what are they made of, is to go and take a piece of them. Now, this is of course very difficult because you need a spacecraft. So an easier way is to wait until a material from these asteroids fall on the Earth. We call these meteorites. I guess you heard this term before. Now you take this meteorite and you take them to the lab, and then you put them under the microscope. You learn what are the minerals and molecules this material is made of. And you can take a spectral measurement, like you see here. And the spectral measurement that you have, you can compare it to the spectrum of asteroids. It's not really a spectrum, it's what we call normalized reflectance, or normalized albedo, or normalized spectrum, reflectance spectrum. This means that, of course, these asteroids are solid, they are not ionized gas. So what you do is observe them, let's say, the asteroid, doing spectral measurements, and then you divide the spectral measurement of the sun. Why? Because the sun, the asteroid basically reflects the spectrum of the sun with some differences that are the result of the material the asteroid is made of. So what you can see here, for example, that this is a metallic meteorite, and this is a metallic iron spectrum. So if we'll have an asteroid with a spectrum looking like this, we'll say, most probably it's a metallic iron. This one is a silicate. This one has some of a rich carbon material. Okay. Does this always work? Oh no, you'll see later on, but it does not always work so easily. So first of all, sometimes it's even hard to do spectral imaging. Like it's even easier to do, let's say, colors, filter B minus filter V, or U, V, VR, whatever. And you can already start to have some classification of the asteroid. So this is an old picture, old graph from the 70s. And very fast, they learned that asteroids can be divided into two main groups, the S ones and the C ones. And so different colors means probably different composition. They found out that this different in colors is correlated with albedo. Albedo means its amount or the ratio of light that is reflected. So let's say white asteroids will reflect most of the solar light. Dark asteroids will absorb most of the light that hits them. So bright asteroids, S-type asteroids are brighter, have higher albedo compared to the C-type asteroids, but they are darker. This is the visible spectrum of a C-type asteroids. Basically, it's flat compared to the S-types, that is redder. You see, you have more signal in larger wavelength, so it means that it's a more red object compared to the, let's say, gray C-type. And this S-type has some kind of feature, if you want, this bump. The C-type is more flat. Compared to meteorites on Earth, they said, okay, it seems like these S-type are more like silicate or stones, compared to the C-types that more carbonaceous materials that are based on carbon minerals. So this is where S and C came from silicate and stone. It's good that silicate and stone starts both with S, so we can use both of them here. Okay. However, you can say, okay, maybe if it was a single planet there in the main belt and what was destroyed, well, at least it was two. One of them, maybe the source of one is S, the source of the other one is C, at least. Or maybe the source is completely different. Okay. Someone wants to ask a question? No, so I'm continuing. Now, another important thing to know, and very soon they add enough details to know, is the spatial distribution or the orbital distribution of these types. So you can see that, let's say, the outside main belt around, let's say, 3 AU from the sun. Yes, the sun is here somewhere. You have more C-types, presumably more carbon material, compared to the S types that they are more common in the inner main belt, yes, around 2 AU. There are other groups as well. Let's avoid them for now. We'll talk about them later on. Now you can say, wait a minute. If this maybe carbon material is farther away compared to these S-types, to the silicate, maybe we can, it's a function of the distance from the sun. So as you go farther away from the sun, temperatures are colder, of course, so more materials can be in a solid state. So if you are closer to the sun, you'll form only metal and then rocky asteroids, then water ice, then other ices like methane or ammonia, etc. CO2. So maybe these C-types are icy bodies, or maybe they are carbon material, so something in between. So we said cousins of comets, so it comes here. Or maybe not. So we need actually to find out that can this spectral type, can we link it to the internal composition of the asteroids and into this thermal gradient of the young solar radiation of the sun, the solar radiation of the young sun. Yes. So this is our question. We need to answer. If you want, if we see maybe if we go back to the plate with the cake, the fact that we see more smear of chocolate, maybe this means that the bottom of the cake is made out of chocolate. So we have more leftovers from this layer, maybe. And of course, we want to use this asteroid in order to, if you want, calibrate where we have more metal, where we have more water ice, in order to know the temperature of the young sun, etc. Okay, so we want to be sure that C-type asteroids, maybe they have a lot of water. Okay. So when we look on meteorites, carbon meteorites, we see that they have about 10%, 20% water inside of them, which is quite a lot. It's really hard to know this in space. Or do C-type asteroids have 10–20% of water? It's really hard. Why? Because our atmosphere blocks the wavelength range where an absorption line of water appears. So it's in area of about 3 micron, 2.7. So in some cases you see it, some cases you see part of it, some cases you don't see it at all because it is blocked by our atmosphere. So in order to know this for sure, one way is to send spacecrafts to these asteroids. Of course, this is always a problem. So are C-type asteroids constituted of carbonaceous material? Can we make this link for sure? So just a minute. So one of the things we can do is to send, again, a spacecraft to such an object, such an asteroid, a C-type asteroid. And in these years, as we are talking, there are 2 spacecrafts that actually are doing so. One is called OSIRIS-REx. This is an American mission to the asteroid Bennu, C-type asteroid Bennu. And another mission is Hayabusa 2. It's a Japanese mission to asteroid Ryugu, C-type asteroid Ryugu. Interestingly, both asteroids have very similar near-Earth orbit. Of course, it's near Earth, so it will be easy to go there. You see it's inner of the main belt of asteroids. They have very similar spectrum, what we call C-type. It's even a subclass of C-type. We call it a B-type. So it's because it's a little bit negative. The slope is negative, but you can see how similar they are and how they are different from other types of asteroids. Maybe you can recognize this S-type here. They also have more or less the same size, a sub-kilometer size. And very interestingly, when the spacecrafts arrived, they found out that they have the same shape. It seems like they arrived to the same asteroid, these 2 spacecraft, which is not the case, of course. Pay attention that this shape is actually common among kilometer size or smaller than that asteroids. You have this circular spherical shape with this ridge across the equator. How come? Why it is relatively common among asteroids? Because these small objects have very small gravity. There are not enough material there. So when they start to rotate fast, maybe this rotation is too fast, and the centrifugal force becomes stronger than the gravity. So the material starts to slide to the equator from the North Pole and from the South Pole as well, forming this ridge. Okay? And many, I don't know many, but we find again and again this kind of shape for this size of asteroids. Okay, so again, they are very similar. They have the same density as well. This is what the spacecraft showed us. So it seems like it's wonderful. In a way, if I can joke and say that maybe it's very poor decision to send two spacecraft to study the same thing. Or is it? Why? What is different? Well, three stuff are different. Well, first, the spacecraft are operated by two different countries. The American mission is more expensive, like 4 times more expensive. But I should say that the Japanese had Hayabusa 1 mission. They also pay a lot of money there. But there is another difference. And this is like, I think, an exciting thing. Remember, the reason to go there is to look for water, to find out, do we have water on these C-type asteroids? Why? In order to make this link, okay? And when the two spacecrafts arrived, started to measure the spectrum from orbit, well, they measure the spectrum. Here it is. Okay, so let's first look at the right, at Ryugu, the Japanese asteroid. We are looking at this water feature at 2.7 micron. I should mention that 2.7 micron this is in near infrared. Okay, so it's our atmosphere here on Earth really blocks this wavelength. And they found a feature here, this observing line, meaning that there is water on Ryugu. But when you compare it to meteorites, these two lines are the similar spectrum for meteorites, there is not a lot of water there. These 3 lines, you can see them here as well. Okay? And you see how small is this observation line compared to these 2 lines. Here, these are 2 other meteorites. They have much more water than these 2 meteorites and from Ryugu itself. And I put this here because these 2 meteorites are actually these 2 guys, the blue one and the red one. And the amount of water there is similar to this black line. This black line is Bennu. This is the American asteroid. You can see that the American asteroid is the same one, this and this is the same drawing, same spectrum. So you can see that the American asteroid, Bennu, has much deeper and larger observation line of water compared to Ryugu. This means that, let's take this off. This asteroid here on the left, Bennu, is much more rich in water compared to Ryugu. And this is crazy because this means that C-type asteroids can have water, but not necessarily. Why? What happened to the water there? Did they become dry, or this asteroid become dry for some reason? Or the water evaporate? Maybe it happened before the asteroid was formed. I don't know. All of these are open questions waiting for you to answer. Water and asteroids are even more interesting because if I go backward here, just a minute, we'll see something else. When we look on the water on Earth, here is Earth. Water, of course, H2O, has a lot of hydrogen inside. Every 2 hydrogen atoms compared to 1 oxygen. Some of the hydrogen will be an isotope of hydrogen, deuterium, D, marked here with D. The ratio of D to H within, I don't know, a glass of water on Earth, water of Earth, is very different than the water we find, or the vapor of water we find on Jupiter, Saturn, Uranus, and Neptune, very different from the vapor water we have on the Sun, on the Oort cloud, on the Jupiter family comets or other comets, interstellar medium. But it's very similar to what? To what we have this green line on a carbon meteorite. It's very similar. And people started to wonder, is the water on Earth coming from impacts of these carbon-based asteroids, the C-type asteroids? If true, and we are talking about maybe 1/3 or half or most of the water on Earth. Where is my water? Is my water? So maybe I'm drinking now a material from asteroids. It would be nice. So if this is true, this is fantastic because it means that water can come, well, not just to Earth, to other planets as well. Maybe it's not just water, maybe it's other material as well, other volatiles, like the building block and other materials like the building blocks of life. So the fact that stuff, I don't know, important stuff like this can travel in space, well, you can speculate a lot of stuff following it. So this is another important thing about asteroids. So let me go forward. Okay, good. Let's see the time. So I have like at least 40 minutes or so. Okay, good. So let's go back to our ability to differentiate, to disentangle between different compositional type of asteroids. So we have here this S-type you saw before, the red, and the C-type in blue. And with time, we find even more material. For example, I showed you before even metal meteorites. We find asteroids with spectrum with this straight line, similar to metal. Are these metal asteroids? Okay, question. Or we have this one. This is the spectrum of Vesta. It's a very large asteroid. We call it V-type. Dagmara, by the way, part of her studies is on these V-type asteroids. But you can see that the differences between them are somewhat subtle. There's a lot of noise. Sometimes if the asteroid is small, the noise will be much larger. And then can you really disentangle between the different types? It will be hard. Even though people made these tools. For example, Bobby Bass is an astronomer in Hawaii. So this is a taxonomy map in order to help us do classification for different types of asteroids. So basically, this is the S-type area, and this is the C-type area, and this is something in between. But you can see that it can be really hard. Can you really distinguish between this SA and A and SR and R? I don't know. For me, it looks all the same. Your signal to noise must be fantastic in order to distinguish, in order to identify properly the composition of this asteroid. So we need to make our life better, easier. One of the ways is to go to a wider wavelength range. For example, near IR. So before I talk with you about 2.7 and 3, the classic near IR is between 0.8, 0.9, all the way to 2.5 micron, like you see here. So this will be the visible. And let me add the near IR. Oh, suddenly, it's so much easier to disentangle between the different groups, to distinguish between them. And suddenly we can see that Vesta here, the purple friend, has an absorption band at around 2 microns. And this absorption band is what we call the pyroxene. So we know that, for example, Vesta has a lot of pyroxene. We'll meet pyroxene later on in this talk. And it's much easier to compare the different groups. So subtle features invisible hint for much larger differences in near IR. Okay, this is good because now we can start comparing different types of spectral measurements of asteroids or spectral types of asteroids to spectral types of meteorites. And here you can see it, we call the asteroid, the taxonomy key, we call it Bass de Meo. Bass is Bobby Bass that did the visible measurements. Francesca de Meo did the IR measurements. And here Pierre Vernazza is an asteroid astronomer from France, from Paris, is he made this comparison. And it's nice, it's a great key. You can say, okay, these S-types are similar to these chondrites, sometimes, not always. It seems that sometimes the unique solutions or unique links are very hard to do. Why is that? Because some reasons. Well, first of all, meteorites evolve while they pass through the atmosphere and while they're waiting on the surface of the Earth until someone finds them. And in that time, their spectral signature can change. Oops, this is wrong. More than that, the spectrum of an asteroid can change with time, and not because of its composition. And this presents to us another a famous paradox in asteroid science. This is called the Ordinarychondrite Paradox. When back in even in the 70s and 80s, people look on a spectrum of asteroids like these S-types here in red, they found out that it's similar, but not exactly the same as this green line, what we call Ordinarychondrite meteorites. So, but it looks very similar. So you can say, is it the same? Is it not the same? So you can see also this blue line, what we call the Q-type. These Q-type asteroids are very similar to the Ordinarychondrite meteorites. So people said, okay, we just need to find these Q-types are very common in near-Earth asteroids. We can't find them in the main belt though. How can it be? Does this mean that near-Earth asteroids are not from the main belt? Does this mean that meteorites, Ordinarychondrite meteorites, and you see the Ordinarychondrites, ordinary means that there are many of them. Aren't they coming from the main belt as well? So we had two options to choose from. When one claim was that S-type asteroids are not Ordinarychondrite, and Ordinarychondrites are not melted, this means that the S-type might be melted igneous body, so they were formed in a very hot place. Very place with a lot of pressure that allowed them to be melted. And these are not not the source of Ordinarychondrite. Another option is no, these are actually the same. This S and SQ and Q and Ordinarychondrite meteorites, they are the same, but for some reason, the surface of the asteroid got changed with time. And we even have a reason or a process to explain this. This is what we call space weathering. The top layer of the asteroid changed. How come? So the process is like this. The idea is that, we actually see this on the moon, so it's not something of a crazy idea. The very small impacts of dust, of cosmic rays, of solar wind particles, they evaporate minerals on the top layer of the asteroids. They evaporate and then they freeze back very fast. But while freezing back, the metal within the molecule leaves the molecule. And now you have these black spheres here. This is nanometer size. And these black spheres make this change in the spectrum of the asteroid, making it redder. Okay? I can hear someone, maybe you could want to mute yourself in order to, so we'll not hear you typing. In this way, the spectrum of these S-types can change. And indeed, when the first Hayabusa mission went to an S-type asteroid called Itokawa, they indeed found, the spacecraft found out that this asteroid is built from Ordinarychondrite, from this green line, even though the spectrum of the asteroid is this S or SQ type. Another spacecraft did it for the asteroid Eros. So this means that indeed the first claim here is wrong. The second one is true. So the spectrum of asteroid even can change with time. So if we go backward to here, so part of the difference between these S-type, SA, SQ, or whatever, to these meteorites is because the surface of asteroid is changing. Okay, Another thing we should remember that these S-types are not melted, is not melted objects. These objects were formed at, let's say, low temperature. And this is important for the next few slides. Okay. Another thing that I want to show you how hard it is to make this link, and I'm sorry that I'm jumping back and forth. Go to all slides. Is this story. What you see here is a meteorite called Al-Makhatasita. This Al-Makhatasita is a place in northern Sudan. What is famous or unique about this asteroid is that it was the first asteroid that was discovered before impact the Earth. This and you can see here the leftovers of the explosion. And this object was measured one in space, and then this guy, Peter Jenniskens, went to collect the meteorite from northern Sudan. And then he was able to compare the spectrum of the meteorite to the spectrum of the asteroid, and to learn what is this meteorite is made of in the lab. So he found out that the main mineral there is uranite, never mind what it is. It's a material, it's achondritic, so material that went into some sort of melting within a differentiated body. We'll talk about it later on. Now we say, and in their paper, Nature paper, I should say, they said that, look, the asteroid has a spectrum, a flat spectrum, and so it's like this F-type, I think it was. And so F-types asteroids have uranite. And this is wrong. Why? Because there are so many different types of asteroids with this flat spectrum. So this link is not necessarily true for all asteroids. Okay, great. So this is a problem, and now I'll go backward. This is a problem sometimes when we try to classify asteroids, you are not really there to touch them and bite them and see what they are made of. You need to be really careful from over interpretation. Okay, and this is especially true for these asteroids with flat spectrum. So all of them are flat. Are they different? Are they similar? It's really hard to know. Okay, in a sense, it's like try to classify animals by their shadows. So you see here ducks and penguins. They have two legs. If we only use legs as a parameter for classification, we think that penguins and ducks are like humans. And I guess you know that this is wrong. Okay. So you always need to remember that this classification, many times we are missing the entire picture. Okay. Now I can continue. Good. So I mentioned that again, these flat spectra, as with flat spectra, we have a question mark on them because they are confusing us. Are they made of the same material or not? So we said that C-type asteroids, those that with water or dried of water, this is a one type of asteroids with flat spectra, but it's not the only one. Another type is what we call P-types, and they are even coming from farther away from the main belt, even from the outside of the main belt. They're dominating the outer main belt, and also the Trojan area, the Trojan of Jupiter. What is this P-type? They are less water or more water, or more other organic materials, carbon materials? Well, we don't know. We only have, the only thing we have is this line. So this mess here of lines, this is C-types, P-types is this one, this green line. And just a minute here. And in order to know, well, we need to send another spacecraft. So this spacecraft called Lucy, and the Lucy mission is going to launch soon going to, actually this year, it's going to reach its destination in the Trojan area in 5-7-6 years from now. It is very ambitious mission because we're going to visit about 6 objects, okay? And these objects are at the Trojan area. And this Trojan area is rich with this also C types and P types and D types, all this, and so therefore you will need to wait, or you will need to invite me again to tell you the difference between these types of asteroids only after the spacecraft will do its science. Maybe we'll find that it's just the same thing, okay, with some differences due to space weathering or other physical process. Okay. Interestingly and annoyingly, another material that is here on these straight lines, these flat lines, is M-type itself, metal. So metal also have spectrum that is very flat. Actually, this green line is not just the line for this P-type, okay, this organic rich material, but also for metal itself, a very similar spectrum. Oh no, how can we know if an object is a metal or not? So one of the things to do is to measure the albedo. So these P types are more dark compared to the metal ones, but it's not always the case. Sometimes the error is too large. Sometimes it's really hard to know the albedo. So this can be a really big problem. And some of our statistics are wrong because we are not able to disentangle between these two types. Okay. And also the slope, we have the slope difference here, but again, the slope can be a difference between some processes happened on the asteroids. Okay. For example, what you see here, this thing here, the black lines is Bennu itself. So you can see that some measurements had different slopes. And you can see that these slopes are here compared to slopes of a meteorite. And actually it's the same meteorite, but the difference between the red and the green and the blue line is the size of the particles in the sample. So as the material in the sample is larger grains, the slope is lower. So sometimes these kind of measurements cannot really tell us what are these asteroids made of. Okay, this one we said. Okay. Why are these M-type asteroids are important, these metal asteroids? Because they are an important factor within the formation of planets. Okay, I see that you have some question now. Okay, I'll read it later on. I'll try to mute you all. Yes, I was managed to do so. Excellent. Good. Okay, let me go back to metal asteroids. So metal asteroids are important in order to know the formation of the main belt, also the solar system as a whole. Where do we find this metal asteroid? How come we have an asteroid that is a metal is like a large fraction of the mass of this asteroid? How come? So we need to remember that if we have an object, a planet, a small planet, let's call it a planetesimal. I guess you are familiar with this term. This planetesimal is large enough in order to be hot enough, dense enough, or as enough radioactive material that increase the temperature in order to melt everything inside. Then iron is heavier, it is sinking down, and other silicates are forming or crystallizing in the mantle area of the planetesimal, and the pyroxene can crystallize in even lower temperature. So this happens in the crust. So this very simple, maybe too simple, model suggests that if we'll take a large body, let's say larger than 100 kilometers in diameter, or even larger than that, it will have, after a time, a metallic core, an olivine-rich mantle, and a pyroxene-rich crust. Now we come and we smashed it, okay, and we destroyed it. And we have many asteroids, some of them from the mantle, they will be rich with olivine. Some of them from the crust, rich with pyroxene, and from the core, they will be rich in iron. Sometimes, yeah, okay. Well, a nice thing or a convenient thing is that the spectrum, the reflectance spectrum of olivine here in black and pyroxene here in purple, they are very different from one another. So even if your measurements have low signal to noise, it's easy to say, okay, this is pyroxene, this is olivine. Olivine is, it's very easy to identify. However, metal, as you saw, it is not easy to identify because it's similar to all these other carbon-based material. And of course, this carbon-based material is not from the depth of a planetesimal. It would be melted and evaporate, and you can see it. So the fact that we do see pyroxene and olivine and let's assume metal asteroids means that we have evidence for differentiation. We have evidence for large planetesimals that existed in what now we call the main belt. How many of them? 1, 10, 100? What were the sizes? Question mark. It's an open question. In order to be sure that these M types, or some of them, are really metal, are they really a core of an asteroid? There is another space mission. This is called Psyche mission, after the name of the target. The target is the asteroid 16 Psyche. Here I put it in more or less a size scale to scale with our moon and Ceres and Vesta. So it's pretty much large objects, about 250, 300 kilometers wide. And this is very metallic. We know that it's metallic also from radar measurements, not just from spectral measurements. A launch is coming soon. The spacecraft will arrive 26, 27, a few years from now. And we want to see how planets are looked from inside. Like nature was kind enough in order to rip off the outside layers and show us the core. And we want to know how different it from the Earth, for example, and many other parameters. Just the other week, a week or two ago, there was a paper saying that, I don't remember if it was 20 or 40% of Psyche is probably metal. So you can imagine how heavy this asteroid is. Okay. So we have some metal. Maybe we have more metal than we think, or less metal than we think, in the main belt of asteroids. But the thing is that it is important because it's open for us another problem, what we call the missing mantle problem. If we take the Earth, the core of the Earth, and compare it to the mass of the mantle of the Earth, we get something like half. Now, if we take all the metal asteroids, their masses, what we think they are metal asteroids, and compare them here at what we call M types, these green lines here. Compare this to all the olivine asteroid, the asteroid rich with olivine from the mantle, presumably, or what we think, yeah, okay. We get much different of a ratio. Okay, it's like 20 times difference. This means that we are really missing those olivine asteroids. So option number one, maybe we don't know the real number of metal asteroids. We think they are metal, but they are maybe not metal. It's a good question. A second option is that something happened to these olivine asteroids. We have some other constraints here. when we look on iron meteorites, we can, from some parameters, we can recognize that they came from maybe 60 distinct bodies. But these mental crust meteorites, it seems like they only came from Vesta, or maybe two other objects. So the source is like much smaller. Here we're talking about meteorites. So we are in a puzzle here. How come we have this difference? So like one option is that the material, this mental material, is somehow get grinded away and we can see it. However, if this is true for this mental material, crust material, how come it is not as true for the S and C? They're supposed to be even softer. So this is a problem. And maybe we don't understand the classic differentiation process. Maybe the planetesimals are not hot enough to crystallize olivine, but can melt iron. This does not make any sense. Well, iron needs higher temperature. Maybe metal actually was not formed in the main belt. Maybe it is formed in the inner solar system, then migrated outside to the main belt. And maybe only the iron did it and not the olivine. But we need to explain how this happen. How can this happen? So, like shamelessly, I promote one of my studies here, and try to give it like maybe an option. When we looked on Trojan asteroids, but not Jupiter ones, but Martian ones. So Mars also have Trojan asteroids. So you see like a leading and trailing Mars on its orbit. It has only like 11 or 13 or so, and like many of them, a very similar group, very similar orbits. So we claim all of them are from the same source. And when we look on their spectrum measurements, it's classical olivine spectrum, what we call the A-type asteroids. And since there are very few A-types, very few olivine asteroids in the main belt, outside, and since so there is very low chance for Mars to capture these A-type asteroids, these mental rich asteroids, olivine rich asteroids. So we claimed that this material is actually from Mars itself, because Mars is differentiated, it has mental, and we can find olivine on Mars. There are sufficiently large craters there that suggest that was a big impact that was large enough to excavate material from the mantle, this olivine from the mantle. And we found a dynamical path from Mars to these Trojan orbits. And it is stable. These orbits, as I mentioned before, are stable. So maybe some of these olivine-rich asteroids, maybe they are from the terrestrial planets themselves. This is also true for the metal asteroids. Maybe they come from differentiated planetesimals that lived a long time ago in the inner solar system and only migrated outside to the main belt. Can it be? Can we make this migration? Can we estimate the number of planetesimals from this kind of measurements? Okay. Good. So this is another question. And the final question, another puzzle, is coming from the distribution of different types. This is made out of this work by Francesca De Meo and Benoit Carey. They basically looked on one of the largest surveys called SDSS, Sloan Digital Survey, Sky Survey. They had like 30,000 objects there, but they only used visible colors. So you already know that maybe we should not trust it completely. And they draw the distribution, the orbital distribution of the S and the C types in the main belt. Now, basically, you saw this figure before here. This is an older figure. But in a way, now you see that, sorry, the old figure is number of asteroids, or the distribution, or the relative distribution of the number of asteroids. And this one, this work by DeMeo and Carey, here we're talking about the mass. And then suddenly we see that we have mass of asteroid C-types and S-types all over. They are mixed. Also these D-types that's supposed to come from farther away. They are mixed. You have all of them everywhere. What caused this spread? Okay. Now we need to take this question, this mixed asteroid composition, and add it to two questions we asked before. How come there was depletion of mass at early times? Why we see only mass that is equal to 4% of the mass of the moon? And the second question, why are the orbits of main belt asteroids so excited? Yeah, high inclinations, high eccentricities. So we showed before that Jupiter can have some, like, clean these gaps. Can it does also this high inclination and high eccentricity and mix all the asteroids together? This is a problem because all this area, yeah, with a lot of asteroids, these are safe area. Can Jupiter, I don't know, endanger or affect this safe area? Well, yes, only if you can move Jupiter. Can we do it? Wait, we have some other constraints. One constraint is the fact that the mass of Mars is very small compared to Venus and Earth. So some material was lost there in this annulus of material where Mars was formed. We also have a special material like the Trojans of Jupiter, the Trojans of Jupiter, irregular satellites of giant planets. So you have a planet, it evolves like this, and it has satellites evolve the same way, and suddenly you have another satellite that orbits completely the other way around. So it was probably captured from someplace. Also, these D-types asteroids, these asteroids are very red, and they appear in the Kuiper belt. How come you see them in the main belt as well? Also, the fact that there is water on Earth that is very similar for the water compared to the water from these carbon asteroids. How come this carbon asteroid impact the Earth? Can we connect all these constraints together? And the final thing is what we called the late heavy bombardment. This event that maybe happened 3.8 billion years ago. In this event, we suddenly see increase in the number of craters on the moon. So the number of craters on the moon decreases with time because there is less material flying around, and suddenly we have this increase. Now I should say that these days we're not sure that it really happened, but let's say it did. So can we take Jupiter and put all the blame on Jupiter? Blame it on the Jupiter. Can we take Jupiter and move it around in order to make this mess in the solar system, early solar system? So this guy, Kevin Walsh, and his companions think that this is possible. So this model is called the Grand TAC. You can, of course, read about it. What they are saying is that in the beginning, everything was in order. Metal and rocks were formed closer to the sun. Then we have the C-types, P-types, D-types. As you go farther away, you have volatiles, more volatiles, but in the form of in a solid shape to make these asteroids. And now, suddenly, for some reasons, but I don't get into them, Jupiter went inside into the solar system, and of course making a mess as due to its gravitational pull. And after he went all the way almost to Mars orbit, he captured the Saturn. It went into a resonance with Saturn and pulled him inside as well. And this caused after a while, Saturn allowed Saturn to pull Jupiter outside. So this is called the tack, like in sailing, when you change the direction of your sail, and then you change your direction. So you can imagine Jupiter on a small sail changing its direction and then going inwards and outward again. And by doing this, everything became a mess. So you can see how the red S types went outside, these blue C types went inside, some planetesimals were lost. These planetesimals hit one another. I forgot to mention the formation of our moon, what was probably formed by a large planetesimal that hit the Earth, etc., etc. So yeah, I say this. So asteroids' orbits are excited as well. Most of the material there is lost, is depleted. The composition are mixed. Drastic mass removal from belt, I said before. Mars annulus loses material, so Mars did not grow as Earth and Venus, and also deliver C types to inner solar system to give water to Earth. This is one story, but as I mentioned before, this late heavy bombardment happened 700 million years, 800 million years after the formation of the solar system. So they actually had a second part of the story, and funny, this second part of the story actually was invented even before this current attack in the beginning of the 2005. So it came to solve another problem, a problem of how you take the KBOs and take material from there inward. So what this model, theoretical model, is called the NIS model, and what they are saying, this model suggests that there were 4 giant planets. The 4 giant planets were much more compacted. Their orbit was much closer to the sun compared to today. Like Jupiter and Saturn were the same place, more or less, but Uranus and Neptune were much closer. And then, due to some dynamical interactions, these push Uranus and Neptune outside. Like you can see the blue and the purple lines outside. And this made a mess and took material from, or these small asteroids, from outside, from the outside parts of the solar system inwards. And basically, it also cleared most of the Kuiper belt as well. Also put these D types that we see in the KBO, put them, allow Jupiter to capture them as its Trojans and these regular satellites. Also, we see these D types at the main belt. And this maybe made the excess in the impacts on the moon, or this large late heavy bombardment event. Okay. So we have these 2 stories of planets moving around, making this mess. If you want, you can imagine them as this person that eat a cake in the restaurant and left for us these leftovers in order for us to understand what was there in the plate. Maybe it was an asteroid. So with this, I'll conclude my talk about open questions about asteroids and how they relate to the formation of the solar system. If you have any questions, please ask them now. And
I think
oh, sorry. Grazina, I'm sorry, I pushed the. Okay, go ahead.
I think that not just astronomers have open questions. Participants of the school have even more open questions, I guess. So
excellent. Yes, questions are good.
So please ask your questions. I wrote to participants that it is better to ask questions after the lecture, because we did not know how much we will have time. So now you can ask.
Yes, don't be shy, please.
Yes.
Let me go through the chat. Maybe there are more questions.
In the chat, I see that participants are thanking you, and
This is always good.
the fantastic talk. I think that everybody agrees.
I have a question.
Yes, go ahead.
How do you know about the you showed a slide when you about the bombarding of the moon.
Yes.
How do you know that date, that period?
We know, okay. You can look at the moon and start counting the craters. This is one. And you can measure the size of the craters. This is two. And then you can date them, or not exactly date, but put them in order. Because if you have a crater and then part of its rim is disappeared due to another crater, you know which crater is younger and which one is older. Okay. Another thing you know, or think you know, or you can try to calculate this from the numbers of impacts, is the rate of impacts. And then you, in this way, you can start a date or try to give a formation age for each impact. Now, in a way, this is somehow relative. Like, okay, I have one, I know what its age compared to other craters. However, you can try to calibrate this, for example, using sample brought from the moon by astronauts. And then you somehow have this map of the age of craters. However, to tell you that this is solid or secure, I cannot. This is why at the past, they thought that they have this increase in number of craters. We call it late heavy bombardment. And later on, we said, wait a minute. Those people that count impacts, maybe we are wrong. So I'm studying asteroids. So when they said, maybe we are wrong. So, you know, you start to be cautious here. So definitely, if you don't need to create this impact during this late heavy bombardment, maybe there are some mistakes in this Venice model, definitely. And did really Jupiter and Saturn and the Uranus and Neptune moved all around? I don't know. Yes, the nice thing about these models, I'm kidding. It's not a nice thing. That they have some kind of initial status. They run the model and they reach current solar system, the current picture of the solar system, current status. And then you ask, okay, maybe you should start from another initial conditions. Do you reach the same thing? Sometimes yes, sometimes don't. So this is like one solution. So to tell you that we know who ate our cake, I don't know yet, but maybe this will be your job.
Okay, thank you.
Sure. More questions?
Hello, this is Dhanraj. I would like to ask some questions.
Please talk louder.
Yeah, this is Dhanraj. I would like to talk these questions. Hello.
Yeah, go ahead.
Yeah. So, Professor, so we have space-based observations from all spectrum, what is present here, right?
Yes, we have spectral measurements of some of the asteroids. So all of the spacecraft that went into like orbit and asteroids were measurements, but the number is not so large. Or should I say, actually, really a few. Okay.
I would like to ask, what is your opinion? Is it realistic to change trajectory of hazard asteroid?
So actually, NASA will try to do it next year with the DART mission. I think you have a talk by Christina Thomas, right? In a few days. It's amazing how, like, it's a big rocket, but it's amazing how small is the effect on the orbit of the asteroid. But if you have enough time, you know, you can, a small motion will accumulate into very large change in the orbit of the object.
So we need to do this much in advance in order to make a larger impact.
Exactly. So we need to have good intelligence in a sense of to collect as much of data as we can and say, okay, this guy is going to eat us in 100 years. Okay, we can do it peace and quietly, you know, no harsh. Okay, see Anila?
Yes, Angelina, please.
Angelina, sorry.
Angelina. But I thought that there is something like a rule that people shouldn't cause any like changes in space, in solar system. Like if you will change an orbit of an asteroid, it may cause almost unpredictable changes in the whole system, at least between asteroids itself, let's say.
So this is a good question. Well, first of all, specifically for this mission, they made all the calculations. This asteroid will not impact the Earth or the moon or something else as a result of this impact. Basically, I don't want to get into Christina talk, but what we're doing there is actually not impact an asteroid, but a satellite around an asteroid. And we're going to change a little bit the orbit of the satellite. And we want to see, will the orbit change, or will the satellite will be like twisted, or its shape will be changed. So the effect there is really minimal. Now, there isn't any space policeman that will tell them, stop doing what you want. In space now, everybody is doing whatever they want, even though there are some space rules. Very recently, by the way, also in America, but in other places as well, the governments wanted to push the industry into or space industry to go into asteroid mining, because some of the material there might be, you know, useful or in space or in Earth, whatever. So I think the Americans have changed their laws, but if you have a company that goes to an asteroid, you can do whatever you want there. So, and the minerals that you will mine, you will extract, are yours. You can have benefits from them. So, if, I don't know, if we'll change the law in other countries, well, what can we do? Yes, every country in space is doing now whatever they want. So we are not yet in the period of when we have a strong police in space or something like this.
So Mike?
Okay. Yes, Mike, go ahead.
Hello, do you hear me?
Yes, I do.
Okay, thank you very much for this excellent talk. My question is concerning the deuterium to hydrogen ratio.
Right.
You mentioned that the asteroids, the chondrite asteroids, have a similar ratio to what we are facing on Earth. And I know from the Rosetta mission that for the Comet 67P Chury, the D2H ratio was 3 times higher. On the other side, on the protoplanetary solar or nebula, this ratio is much lower, for example, from Jupiter and Saturn. So my question to you is, how does this fit together, and how are what are the processes which change this ratio?
So I'm not an expert in these issues, but I think that some of the difference is like the distance from the sun, or basically temporal temperature differences. I'm not sure about it because like Jupiter and Saturn is very similar to the sun, and then comets is actually higher and even higher from the Earth. So I actually have no idea, but this is a great question for a chemist, I guess. So it's something that maybe I will look for it. I'll send the answer for